In section 4.2, Ramsey's theorem and Ramsey theory, we start by talking about the party problem. So the party problem basically says that within a group of 6 people, if you know that every pair of people in that group is either friends or enemies, then there must be a group of 3 mutual friends or 3 mutual enemies within that group of 6. This shouldn't really necessarily be obvious right off the bat. You could maybe try to play around with it and say, well, let's say person A and person B are friends and person C is enemies with A but friends with B. Sort of just keep adding people in and see if it's possible to construct a group where this property is not the case. But you'll have a hard time actually coming up with an example. So to prove that this is actually the case, that in any group of 6 people, you're guaranteed to have a group of 3 mutual friends or 3 mutual enemies, we're going to model it with a graph, and we're going to use something called edge coloring. So in the last section, we colored vertices of a graph. This time, we're going to be coloring edges of the graph. So we're going to consider K6 a complete graph on 6 vertices. The vertices represent the 6 people in your group. And we put an edge between every pair of vertices because every pair of people is either friends or enemies. So we'll color a particular edge, say VI, VJ, green if those 2 people are friends, and otherwise we'll color that edge red if they're enemies. So essentially what we're going to prove is that for any coloring of the edges of this graph with either red or green, right, some combination of red and green edges, we're guaranteed to have a subgraph, a complete subgraph that's either all red on 3 vertices or all green. In other words, we can find a red triangle or a green triangle. Right, so just as a note, this is what we're showing. We show that for any, we call it a 2 coloring because we're using 2 colors, red and green, of the edges of K6, there is either going to be a red triangle in there. By triangle, I just mean like a K3 graph, or a green one. Okay, so how do we prove that? Well, let's start with this vertex V1. Consider vertex V1. This is representing some person at your party. Well, V1 has 1, 2, 3, 4, 5 neighbors. The degree of V1 is 5. And each one of these 5 edges is going to be colored either red or green, which means that there's either going to be at least 3 red edges or at least 3 green edges. You couldn't have 2 or less red and 2 or less green because that would only account for 4 edges. So by the pigeonhole principle, either V1 has at least 3 red edges that are incident with it, or at least 3 green. Maybe they're all green, maybe they're all red, but that would still satisfy this. It's just saying you're not going to have only 2 red and only 2 green coming out. You have at least 3 of one of those. So assume without loss of generality that at least 3 edges that are incident with V1 are green. I say without loss of generality because we could go through and make this exact same argument if they were red, just swapping the roles of red and green. So it doesn't really matter. Just assume without loss of generality they're green and know that the argument would work out the same way if at least 3 were red. Okay, and furthermore, let's say that V1, V2, V1, V3, and V1, V4 are green. Again, this is a without loss of generality statement because maybe it's actually V6 and V5 and V3 that are the green edges. But in that case, you could always just relabel these, right? Renumber the people along the outside so that the 3 green ones are here. Right? The way that we draw this doesn't really matter. So let's just assume, without loss of generality, that these 3 edges are green. This one, and this one. Maybe these are also green, maybe they're red. doesn't really matter. This is enough. To know that these three are green, we'll claim that this is enough to know that we're guaranteed to have either a green triangle in here or a red triangle in here. So why is that? Well, there's sort of three different ways we could end up with a green triangle. If V2 and V4 were friends, we would have a green triangle right here. If V4 and V3 were friends, we would have a green triangle here. And if V2 and V3 were friends, we would have a green triangle here. Right? So if any one of those pairs of people are friends with each other, if either V2, V3, V2, V4, or V3, V4 are green edges, right? If even just one of those relationships are friendships, then we will have a green triangle. And we're done, because that's what we're trying to show. We're trying to show that this graph has a green triangle in here somewhere. Okay, but that's not necessarily the case. Maybe those three people, maybe none of them are friends with each other. Maybe they're all enemies and they hate each other. But if that were the case, that would make this edge red, and this edge red, and this edge red. And so you get a red triangle. So otherwise, V2, V3, and V3, V4, and V2, V4 are all red, and we get a red triangle. Right, so in either one of these cases, we're able to conclude that there is a group of three mutual friends or three mutual enemies. And again, if we had been wrong, and if maybe actually, V1 had three red edges coming out instead, we would make that same argument but swap the rules of red and green, and it would work out exactly the same. Okay, so this proves that within a group of 6 people, there's guaranteed to be a group of 3 mutual friends or 3 mutual enemies. And a good follow-up, which is something you played around with in the warm-up, is that going to be true in a group of 5 people? And hopefully you found that the answer is no. So in a group of 5 people, right, if we were to try to model this with a K5 graph, it's not necessarily the case that you're guaranteed a group of 3 mutual friends or 3 mutual enemies. And the reason for that is, well, you could label all of these relationships around the outside as enemy relationships, and all of these relationships going across the circle here as friendship relationships. And you won't have any red triangle or any green triangle embedded in this graph. And so it's not the case that you have 3 mutual friends or 3 mutual enemies. Now, Ramsey's theory sort of generalizes this to larger cases, to larger complete subgraphs. So the Ramsey number of P and Q, where P and Q are some pair of natural numbers, is defined to be the smallest integer n, such that every 2 coloring, so every red and green coloring, of the edges of the complete graph on n vertices is guaranteed to either contain a red K3 induced subgraph or a green KQ induced subgraph. Okay, so this is essentially saying, this is what we proved in the party problem, that R33 is equal to 6. Because the Ramsey number, in this case 6, is the smallest integer n, 6, such that every 2 coloring of the edges of K6 contains either a red K3 subgraph, a red triangle, or a green K3 subgraph, a green triangle. So we proved in the party problem that R33 is 6 because we showed that every coloring is guaranteed to have a red or a green triangle. And we also showed that it can't be any less than 6 because it's possible to construct a K5 graph with an edge coloring such that there is no induced K3 red triangle and there is no induced K3 green triangle. So R33 is equal to 6. Ramsey was a mathematician who really got this whole branch of combinatorics started, this branch of Ramsey theory. It wasn't his intention. he died very young, and in his proof of Ramsey's theorem was really just incidental. It was sort of more of a lemma that was used in some larger logical argument, but it spawned its own very interesting branch of mathematics in its own right. And so what Ramsey's theorem says is for any k greater than equal to 2 and any positive integers n1 through nk, so in this case n1 through nk, these are going to be your colors. So we were looking at 2 colors. Ramsey's theorem is more general. It says you could have more than 2 colors. Then there exists some larger positive integer n, your Ramsey number, such that if each edge of kn is colored with one of those, these are the colors, 1 through k. Then for some I between 1 and k, there exists a complete subgraph k and I, such that every edge of k and I is colored I. Right, so this is extending the Ramsey number that we defined on this page, so that it's not just P or Q. You could have multiple different sort of subgraphs that you're looking for. P, Q, R, S, or for any number you could do this, right? So you don't have to worry too much about the very specific detailed stuff or the formulation of Ramsey's theorem. The important thing to really remember here is, in essence, Ramsey's theorem is just showing that for any sufficiently large unorganized structure, so any sufficiently large big set of n vertices with all sorts of different colors connecting them, you can find an organized substructure of any size. That's the idea behind Ramsey's theorem. It's really sort of interesting and surprising, and it's really, really hard to find these numbers. So his theorem guarantees that some large enough n exists that will satisfy this, but it doesn't tell you what the Ramsey number will be. It's not a formula. And in fact, in general, finding Ramsey numbers is very, very hard to do. And there's a very famous and prolific mathematician, Paul Erdős, who stated at one point, I'm not sure where he stated this, but this is an Erdős quote: "Suppose aliens invade the Earth and threaten to obliterate it in a year's time unless human beings can find the Ramsey number for 5 red and 5 blue." So essentially, unless humans can find R55. Well, we could marshal the world's best minds and fastest computers, and within a year we could probably calculate that value. If the aliens demanded the Ramsey number for red 6 and blue 6, in other words R66, we would have no choice but to launch a preemptive attack. That is to say, R66 is so hard to compute that it's basically not going to happen in our lifetimes. It's just too hard to do, and people who study Ramsey theory work more on finding sort of ranges for these Ramsey numbers. It can say that R66 is somewhere between 140 and 270. I don't know if that's what it is, but it's something like that. And so the work that's being done in Ramsey theory is often sort of trying to shorten that range, make it just a little bit smaller. But actually computing the Ramsey number itself is very difficult to do. But for small numbers, we can sort of do it by brute force, the same way that we solved R33 in the last page. So in the next video, we'll go through a couple examples of that.